Welcome to ECE 340's final exam review session. We're in the last leg and you're already into finals week. Hopefully things will go smoothly for you. Our final is scheduled for Wednesday from 1 to 3. It's not a Tuesday or a Thursday. It's Wednesday at 1 to 3 in the normal room that we've been having our lectures in. I will have office hours the morning before the final. If you have questions over the weekend or before that and you want to try to email those to me, you can try to send me an email and we can see if we can get those resolved via email if that works for you. The final exam is comprehensive. I have provided a list of topics. I would consider that to be tentative, but it's pretty long. It's about 85 lines of material, but I think it's all collected. It's coming from these chapters in the textbook, B1, 2, 4, 6, 7, 8, and 10. Not a lot in 8. 8 is the Nyquist, and you really just need to know about what is the Nyquist frequency, what's aliasing, what are the apparent frequencies, depending on how you're sampling. I've underlined the chapters that are the key chapters, 2, 4, 6, 7, and 10. 10 is the state space. All the other is pretty much the analog material, with chapter 2 being this, how do you classify signals and systems. 4 is Laplace transforms. 6 is Fourier series, and 7 is Fourier transforms. That's the chapter weighting, or that's how it's grouped. And the process for what you can bring to the exam is consistent with what you've done all semester. You get one more sheet of notes. You can bring in a copy of Laplace transforms, meaning you now have 5 pages that you have available to you during the final exam. You might want to bring a calculator. I don't know how critical that will be, so don't get too hung up if your batteries die, but you can have a calculator and something to write with. I'm simply going to try to walk through some of the topics that we've covered this semester, but remember this class, I've been referring to it as signals and systems, and if you keep this in mind, hopefully that will help you if you start to wonder what's going on or what's happening. Just try to remember that you are dealing with signals and systems, and in particular, if you now have an input that might be labeled as x, it could be little x of t in the time domain, it might be then its transform in the S domain or the Laplace setting. You now want to process that through some system, and that system could be anything. In this class, we've been specializing that to be a circuit or circuits, but then that also produces this output signal y of s, and it's nice to have a feel for how those signals and systems are connected or related, and how you can be thinking of those. If you had the signal represented in the time domain, connecting it with what we've done fairly recently, you might have a pulse that has a pulse width. In this case, it's actually 1 unit long, but this could be now your x of t of amplitude 1. You might want to push that through a system, or maybe that's some information content, and you're now pushing it through a communication channel, and your communication channel has an impulse response h of t. It would be nice to know how is that channel going to impact this pulse x of t? Am I going to see the same looking behavior y of t at the output? This is obviously then in the time domain. One way to find the true solution, a or y of t at the output, would be to go ahead and convolve those. And you need to be able to do that. You could be thinking about what's going to be appearing at the output if you looked at what's happening in the frequency domain. And what's happening, or what does the frequency response of little x of t look like in the frequency domain? What's a pulse give you? That's now this sync waveform, and that now is, let's say, as a function of omega. With this particular point, the first crossover is 2 pi over tau. And this one is then minus 2 pi over tau. And we've sort of agreed that even though the frequency content of that pulse is infinite in extent in terms of it contains all the frequencies, this picture sort of tells us where the most of the majority of that energy in that pulse is occurring. And that's occurring at a frequency omega of 2 pi over tau, which in this case is just the 2 pi, with tau being equal to 1. That now tells you a little bit more about what's happening in terms of the frequency content of your input. If you now wanted to say, well, how is that going to be impacted by my system? Now it might be nice to know what the frequency response of h of j omega is. If it was this exponentially damped system, then maybe it looks like this. And you might want to know, how is this frequency here related to the frequency content in your pulse? And if you are now having a very narrow bandwidth in terms of how many frequencies are passed in your system, in your communications channel, or in your filter, then that's going to be related to this frequency content in your input signal x of t. You could also, so this is one way of thinking of it in the frequency domain. You could also look at this in the Laplace setting, in another frequency domain. If I said Laplace transform little x of t, what would that look like? Or if I now said, whoops, that doesn't do anything. If I cover up the screen, does it? If I said, what if this started here and just never finished, what would that be? And maybe we shifted this to where it didn't start at minus 1/2, but it started right at t equals 0. Then what kind of an input do you have in your system? That's just a step, isn't it? So in the frequency domain, that would be 1 over s. Well, that's really what you have. You have a step that's advanced by 1/2 of a unit, and then you turn it off. Meaning in the frequency domain for x of s, you have this step, but if you now shift it in time with this advance, that's like multiplying or scaling by e to the s over 2, where it's now this advance, so it's now 1/2 times s. Then you simply take away or turn off that step, with a step occurring 1 time unit later, which is now this delay of 1/2, and now we have a minus 1 over s e to the minus st. That's the Laplace expression for x of s. If this is now a first order system, h of t, let's say this is now some e to the minus alpha t, what would you have for h of s? You now have a 1 over s plus alpha. And you could then find the total solution. Again, going back to the very first picture, you now know that the product of transforms in the S domain give you the Laplace transformed output, and if you needed that in the time domain, you need to know how to perform this inverse Laplace transform, which if it's polynomials, you can now find the roots and just do the inverse, the partial fraction expansion to obtain that y of t. Questions on that sort of general picture of what's going on in the class? Now I can break out onto all of those different pieces and focus a little bit more on different aspects of what we've done. And if I may sort of jump around in terms of topics. This one is maybe the most recent, but maybe it's the one that you're not yet as comfortable with. But based on the Fourier transform, you need to be able to understand the definition and apply that to find either the Fourier transform of a signal or the inverse Fourier transform of a frequency response. You could do that by understanding the pairs, and that's table 1 in chapter 7, which is on page 702. It also might be nice or helpful to know how to apply the operations or the theorems. It depends on how you want to label that. That's now table 7.2 on page 715 in the text. And you should be able to sketch the magnitude and phase of this frequency content given to you by the Fourier transform, and also know how to obtain the energy in a waveform or in a signal by using Parseval's theorem. If you're asked for the total energy, a lot of times it's easier to work in the time domain, but if you're wanting to find the energy in a particular frequency band, it's nice to be able to work that in the frequency domain. Let's look at an example of using these operations in the Fourier transform sense. Suppose that somebody tells you that x of t gives rise to the following, I'm running out of room, so I'm going to say x of t gives rise to x of w, and suppose that x of w now is sine of 2 omega over omega. Maybe they tell you that. Maybe they don't even give you x of t, but you should be able to find x of t. And based on that sine of x over x, in a sense, you know you should be getting a pulse out in the time domain for little x of t. But now let's say that they ask you to find the Fourier transform of y of t, where little y of t, the time domain signal, is actually related to the time domain x by 3x of 4t minus 5. And now they want to know what is capital Y of omega. This is now going to require that you apply several of these theorems in terms of transform relationships, and how do you now obtain capital Y of omega given capital X of omega, knowing how the time domain signals are related. If we now rewrite Y of t, we have the 3. That's simply a scalar multiplication. Wow, it's Friday afternoon. And I haven't had 2 finals yet, have I? Maybe I have one after this. So here's 3. Then we have x, and we need to manipulate the argument of x. We need to pull out the scaling and really the amount of time shift that's in there. So if I factor out the 4 from both terms, I have t minus 5 over 4. So that this 4 is representing a time scaling, and there's a time scaling theorem. The t minus 5 over 4 is saying that there's a delay involved, and this is then a time shifting operation. What you want to now be able to do is apply those 3 relationships relative to the time domain signal and how those translate into the frequency domain from those transform tables. The scalar multiplication is the most straightforward. That one just scales everything by 3. But now if we have this time scaling, time and frequency are reciprocal quantities, and now that's impacting the capital X of omega relationship. And in particular, we now have to divide by 1 over the absolute value of the scaling of the time. And now, in terms of the frequency content, we divide omega, the frequency, by 4. This little piece right here is due to the scalar multiplication. This piece is due to the time scaling. And then what happens when we shift in time? In the frequency domain, or in the Laplace domain, that was e to the minus tau sub 0s. And it's similar here, where s is now j omega. This is now e to the minus j omega 5 over 4. So that this term is due to the time shifting. And you're almost there, except now you don't want, whoops, what am I doing y of s? I told you it was Friday. That should be y of omega. Now we have y of omega is going to be 3/4, and we simply replace whatever we had, wherever we had omega in the capital X of omega, we replace all of those omegas with omega over 4, which now says that we have sine of, what did we start with? 2 omega, so we have 2, and then we replace omega with omega over 4. And downstairs we had 1 omega, and we replace that with omega over 4. And we have e to the minus j omega over 5/4, or times 5/4. And now we could simply do some algebra and clean a little of that up. These 4s conveniently cancel, and we basically have this sine of omega over omega. We now have a 2 down there, and if we wanted to introduce the sinc function, where that's now an omega over 2, maybe we put a 2 there and a 2 there. And we have 6 times the sine of omega over 2 over omega over 2, e to the minus j 5 omega over 4. And if we wanted to, I guess we could probably pull that omega over 2 out also. Questions on that? So that would be, the question was, do we need a table? And that's what needs to be on your crib sheet. If you want that table, I'm not going to provide it for you. That would be table 7.2, which would be the transform operations. Table 7.1 would be how to transform particular signals or systems and obtain their Fourier transforms directly. So you may want both of those tables as a part of your crib sheets. That's why I'm giving you one more crib sheet. Should have wished those guys good luck on their final, if they might have one starting at 6. Hopefully they got a good night's rest. Now you also need to know how to work with the sync or with the impulse. And how to bake, right? Or these sifting properties. For example, if I had something that was 4e to the minus 3t delta of t minus 2, what is that actually equivalent to? It's only going to be active when the argument of that impulse is on. The impulse is only going to be on at when t minus 2 is equal to 0 or when t is equal to 2. So this you could rewrite as evaluate that at time t equal 2. And now maybe that's easier for you to think of. E to the minus 6 is pretty small. But you now have, that's the weight on this impulse. The impulse is still infinitely tall or infinitely fast. But if you now had that impulse underneath an integral or inside an integral, let's say that we now had e to the minus j 2 pi t delta of t minus 1 dt, what's the result of that integration? So now we have to worry about this piece of our integrand and what its value is when we evaluate that when the impulse is on. And that sifts that information out of your integral so that you now have this e to the minus j 2 pi t with t replaced with when it's active, which is t equal to 1. Those are really some quick ideas relative to Fourier transforms. Let's talk now about Fourier series. And again, with a Fourier series, when does this come into play? When are we worried about a Fourier series? When we have a periodic waveform. And from that periodic waveform, you need to be able to find the fundamental frequency or the period. And you should be able to have access to all of the definitions of the different forms of the Fourier series so that you could, and that's another table, I think table 6.1 gives you the formulas and the relationships between those different Fourier series representations. The Fourier series give you a little different frequency content. Now you're simply looking at discrete frequencies, the fundamental and the harmonics, meaning you now are looking at these line spectra. And I might ask you to find the power in some frequency interval by means of Parseval's theorem. If I now gave you an example, suppose that I said x of t is equal to 2 times the cosine of 4 over 3t minus 30 degrees plus 5 cosine of 6 over 15t minus 60 degrees. First thing you might want to know, and now I might ask, find the Fourier series of that x of t, or I might say, can you tell me, find the fundamental frequency if it exists, and if it does, what harmonics do these two pieces of x of t represent? What's the frequency of the first one? Let me just call it omega sub 1 for the first component. So this is not hard, but you just have to kind of put it all together. That's just 4/3. So a little bit more than 1 1⅓ for omega sub 1 in radians per second. Omega sub 2, 6/15. And that one's now a little bit more than 1/3. It's a little bit bigger than 5/15. So you now have something a little bit more than 1/3 in frequency and a little bit bigger than 1⅓. And now you're asking, okay, are those harmonically related to some fundamental frequency? And we have this neat little procedure for finding those. We could say our fundamental frequency is now the greatest common factor of 4/3 and 6/15. Or that's now the greatest common factor of the numerators and the least common multiple of the denominator pieces. So that now for the greatest common factor, we can factor those two pieces. And we can factor the denominator terms. First one is prime, the next one is not quite prime. But what's the greatest common factor now in the numerator? We have that looks common with that one, doesn't it? So we have 2, or 1 times 2. And downstairs we need to find the least common multiple. So we pull all of those pieces out. We actually end up with pulling all of those least terms out. We have a 1, a 3, and a 5, or we now have our fundamental frequency is 2/15. And now we need to say, okay, with omega 1 and omega sub 2, what were they in terms of harmonically related to omega naught? Or you could say, with respect to omega sub 1, which was this value of, what was it, 4/3, this is now 2/15 times n1 is equal to 4/3. Or n1 better be an integer, which is 4 times 15 over 2 times 3, and we can clean that up a little bit. And we now have 10 for n sub 1, or that omega sub 1 is now the 10th harmonic. We could also look at what omega sub 2 represented. That was 6/15, and that's now some integer multiple of the fundamental, omega sub 1, or omega sub 0, I should say. We can now solve for n sub 2. The 15s, well, let me just go ahead and do it. The 15s cancel, the 6 and the 2 simplify down, and now that represents the third harmonic. In that original signal then, x of t, we didn't have the fundamental. It wasn't there, but we had the third harmonic and we had the 10th harmonic. Those were the pieces that were there in little x of t. And I could ask you now to draw the line spectra. And you would then have to either say which one you're going to sketch, or you might ask, and I might say, well, use your best judgment. And then it's up to you. You could do the compact trigonometric, or you could do the complex exponential. Compact trigonometric, we only have to worry about one side, or the positive frequencies. I could do this in terms of harmonics, meaning here's 1, 2, 3, 4, 5, 7, 9, and 10. Wow. Running. This could be now C sub n. And what would you sketch here? Now if we go back to our original x of t, so this was representing our third harmonic, wasn't it? That's lower in frequency than this 10th harmonic. So the third harmonic has an amplitude of 5. We can go here and say, okay, that's now 5. And the 10th harmonic was an amplitude of 2. And that's their coefficient. And that's the magnitude behavior of your signal. Then you could sketch theta sub n. At these different harmonics. For the third harmonic, that had an angle of minus 60, and for the 10th, it had an angle of minus 30. Meaning now I'm down here. And if I wanted to, you could have labeled these in terms of the frequencies. This is now 6/15, And this was this 4/3, and that's with respect to omega. And if you wanted to, and just remind people, you could say, oh, omega naught, which was the fundamental, was this 2/15 radian per second, if you wanted to keep track of the harmonics. Yes? So now if you have a negative, I think the question was if I was up here and I maybe had a -5 cosine of 6/15, you could either pull that minus sign into your phase and represent it there, but I think the question was, do I pull it in as a -180 or a +180? And it really doesn't matter. I've just sort of, coming from a controls background, I kind of like to have a phase shift representing a delay, so I usually use it as a minus. But sometimes people might say, I want that angle to always live between plus and minus 180, and they may shift in a plus 180 just to make it smaller in absolute value or absolute magnitude in terms of the angle. But it really doesn't matter. They're equivalent. Does that answer your question? Now what could I ask you? I could say that's the input, but now I want you to process that input through a system, h of t, and produce the output y, and I want to know what's the power in the third harmonic of y of t. What if I ask for the power in the fundamental or the first harmonic in y of t? Yes, you can shake my hand at the end of the exam, right? Because there was no fundamental. Well, I have to tell you what h of t is, but if I'm drawing this block diagram, I'm implicitly telling you the system is a linear time invariant system. If it's a linear time invariant system, now I can walk over to the trash can and shake it, right? Which means that x of t is exciting that system at omega 1 and omega 2. It's only exciting it at the third harmonic and the 10th harmonic, and those are the only two harmonics in the output that you're going to see. Since the system is linear and time invariant, you're not going to change the frequency as it passes through the system. If it was a nonlinear system, if you had a squaring operation going on, then you might see a frequency that was twice what you started with. But here we're playing with linear systems for the majority of this class, or for all the class. And now let's say that somebody says, oh, the impulse response of your system is given by little h of t as e to the minus 1/2 t u of t. And they now say, what's the power in the third harmonic of the output? You could find the power of the third harmonic in x of t. What's that? It's the amplitude squared divided by 2. So we have 25/2, or 12.5 watts. Now we might want to compare that to what we have at the output side, where the system is now this h of t. And what does this h of t represent? What's a quick way of thinking of little h of t? What kind of a system is that? Can you see the Bode plot for that system? If you can't today, hopefully you can by Wednesday. Right? What's the transfer function? What's the Laplace transform of little h of t? What is capital H of S? E to the minus 1/2 t is stable, isn't it? That one's decaying, so when we have stable, what do you know the poles are going to be? They're going to have negative real parts. So if you start questioning, is that a minus, is it a plus, start thinking through what should it be. You know that this is well behaved in the time domain. It's exponentially decaying. So you should have poles where? In the left half plane, which means that the real part of these poles better be negative. Does that help? So if you're starting to question what's happening, you should be able to sort of think your way through it in terms of what's going on. Now, what do we want? Does this even give us any helpful information, this capital H of S? Am I just chasing a rabbit? So now if we're in sinusoidal steady state, well, we're assuming that this x of t has been applied forever, aren't we? So now we're going to assume that this system is now in a sinusoidal steady state setting. And what do we know about this system's behavior in the sinusoidal steady state? You could draw that, couldn't you, and start begging for partial credit. Is that helping? What are we after? I said the third harmonic, which was 6/15, wasn't it? So now we would be interested in, and this isn't necessarily, my horizontal and vertical axes are not consistently scaled. That 6/15 is just a little bit bigger than a third, and this one's a half, so I've messed it up. And meaning if you had your protractor, you would want to make sure your x-axis, your horizontal, and your vertical are at the same scale if you're going to get a reasonable angle or accurate angle. But if you do it on your calculator, you can let the numbers do the talking. But now you're interested in that length and, well, in this case, you're only interested in the length, but you could find this angle for information. The frequency of interest is this omega sub 3, which is the third harmonic of omega naught, which was the 6/15, and we can now say, well, what is h of j 6/15? So now we simply replace s with j 6/15, and we could now write the sinusoidal steady state expression for the output for the third harmonic. The third harmonic started with a magnitude of 5. Its amplitude now gets adjusted by h at that frequency of interest, 6/15. We haven't changed the frequency. That's still omega sub 2, I think is what we were calling it to begin with. Minus 60 degrees, and if we needed it, which we really don't, but I'm going to do it for completeness, minus the angle of h of j 6/15. Five times the magnitude of a complex number is just a number. And that's the amplitude of that third harmonic in the output. So if the notation, if I say what's the power in that third harmonic of the output, I can now just use the formula. That's the amplitude squared over 2. And if we needed to, we could sort of do this. Whoops, what was that? 1/2? So now we have 1/2 squared, which is 0.25. This is a little bit more than a third. That's 0.3. So we have 0.5, let's say, down there. Then we take the square root of that and then divide into that. If you do that, that ends up with 1 over 0.64. Can't read my own writing, which is now this 1.562. And that now scales to 5. Questions on that? And do you see how I can start playing with a lot of different features of what you have available to you? Which is a good reason for learning the circuit analysis or the Laplace step. You'll need to be able to do Bode plots, and what if I give you a transfer function, you should be able to pull a lot of information off of that transfer function. One of those is the system order. You can sketch, and you can also sort of give the magnitude and phase characteristics. Meaning, what are the slopes in terms of the magnitude at low frequencies? What are the slopes at high frequencies? And I would like to think that you know how to do that. If you had a pole at the origin, that would be low frequencies. And what's the slope going to be doing at low frequencies? Now, let's say you had one pole at the origin in your transfer function. Now you're coming down from above, right? On your left, and you're just sloping for low frequencies. You could also look at limiting values in terms of the phase and even slopes potentially at both extremes again, low frequencies and high frequencies. If you now had a pole at the origin, one pole at the origin, what's the phase at low frequencies? It's that minus 90, isn't it? And you could even look at that on your S domain. You could plot your poles and zeros and say what's contributing the most phase at these small frequencies. And that pole at the origin is going to give you that minus 90. You should be able to play with block diagrams and relate those to transfer functions and or state space representations, and go back and forth between those. With the state space representation, how is the order indicated? Or what could you look at and quickly determine the order of your system if somebody gave you a state space representation? You might look for the number of state variables or the dimension of your A matrix, either the rows or the columns of the A. The A matrix is square. But the order is going to tell you how many state variables you have. And in terms of state variables in an electric circuit, how are you going to find those? So these are the L's and the C's, aren't they? Where the L's are going to be related by Eli and the capacitors are I's in terms of their time domain behavior. V is equal to L di dt for the voltage current relationship of an inductor. I is equal to C dV dt for a capacitor. And you should be able to find the dimensions of all of these matrices. Where the matrices should be compatible, meaning A and B are the same height, same number of rows. They don't necessarily have to have the same number of columns. Number of columns in B represents the number of inputs you have in your system. The output matrix C could be short and wide. The direct feed-through matrix is now going to be as tall as the number of outputs that you have, or have that many rows, and it's going to be as wide as the number of inputs that you have. What about stability? And we've been talking a lot about BIBO stability. If I gave you H of S and said it's equal to the following, 1, and then divide that by this denominator polynomial that's been factored into S plus 4 and S squared plus 3 squared. Is that system BIBO stable? I didn't tell you you could. I'm not sure that I want you to, but if you had a coin at the final, you could flip it, right? Have a 50-50 chance. Is it BIBO? Actually, you better have more than that, because now you can factor this or find those. It should probably be factored in terms of quadratics. Now, those quadratics may be 2 real roots, so you'll want to know the quadratic formula if you don't have it. But now, if you're used to looking at this, hopefully you're now seeing that that second factor corresponds to poles right on the imaginary axis. And what does that mean in terms of BIBO stability? Good or bad for BIBO? It's bad, isn't it? Because now I could go shake that trash can at that exact same frequency and cause an unbounded output. And for that reason, then, you should be able to give me the input that would result in an unbounded output. What would that look like? Cosine of 3t would do it, wouldn't it? Because your poles are at plus and minus J3. All you have to do is hit it at that exact same frequency and you've got problems. You should be able to do convolution, flip and slide, and tell me what it is at a particular point, or give me all the different regions. Where is the overlap pattern different? All of those kinds of ideas and concepts you should be able to perform. the Nyquist frequency. What's so special about the Nyquist frequency? If you had to sort of catalog that in just a couple or three words, what would you say the Nyquist frequency gives you, or what's special about the Nyquist frequency? It's the smallest you can sample and still recover all the frequency content without changing the frequency content if your system that you're sampling is band limited. Meaning if you don't sample at the Nyquist frequency, which is what? What is the Nyquist frequency? It's 2 times the highest frequency. So if you have a band-limited signal, you can now identify the Nyquist frequency associated with that. And if you don't, then what happens? Then you get this beast, don't you? Aliasing. And what's a way to determine what frequencies you will see when somebody gives you a bunch of sines and cosines and then they say you're sampling at this particular frequency? What's the first frequency you might want to think about? Folding. You now fold your paper in half. And what's this folding frequency? That's just 1/2 of however fast you're sampling. And if you have aliasing, that sampling frequency is less than the Nyquist frequency. What will you see, or what are the apparent frequencies? Those are now going to be given to you by the original frequency f adjusted by some integer multiple of the sampling frequency f sub s, if that's in, let's say, hertz. Where this apparent frequency, you find that such that it's between that folding frequency. This is somewhat all related to what we've done with MATLAB in terms of sampling. People are always usually asking me, well, how are you going to do a MATLAB problem on the exam? Well, I could ask you a sampling question relative to simulating something. For example, I might say, how fast are you going to sample? Or how long are you going to sample? Or what's the duration of your simulation? Suppose I now gave you y of t is equal to 4e to the minus 2t cosine of 5t plus 2e to the minus 6t cosine of 4t. And I said, how fast are you going to sample that to give me a reasonable representation of that signal, and for what duration of time are you going to sample? And now you really have two things going on, don't you? When you have this signal, you have a decay rate, which gives you a speed, and you have an oscillating piece that gives you a speed. and you want to, and you have that in this example, you have it twice. You now need to say, how fast would I need to sample based on these exponential decays, and how fast would I need to sample if I just had this sinusoidal behavior, and then take the smallest of those. Does that make sense? So how fast would we sample? We, so we should be thinking about two different things, really. We have the time constant issue. So if I look at that first one, the first term, I could say 2 tau 1 is equal to 1. Or tau 1 is equal to 1/2. And the second one is now, whoops, it's now 6 tau sub 2 is equal to 1. Or tau sub 2 is equal to 1/6. And which of these do you worry about? Or you could find sort of the sampling rate determined from each if you wanted to. You could say, oh, if I was just looking at tau 1, then I would say tau 1 over 10. And that's now this 1 over 20, which is 0.05. If I looked at tau sub 2 and took 10 samples in that time constant, I now have 1 over 60. What's that going to be? So I now have 1 over 20 times 3. I've just done the 1 over 20. That's this 0.05 divided by 3. And 3 I could represent as can I do that any weirder? So this is roughly, I guess it's roughly here. So that now I'm looking at, if I just worried about the time constant piece, my tau, I would be looking at the minimum of 0.05 or 0.015. But I also need to worry about these oscillating pieces. And I really can just pick the quickest one. I have omega 1 is equal to 5, omega 2 is equal to 4. I could just concentrate on that one, couldn't I? So that now the tau due to omega, I have omega 1 is now 2 pi over T1. So that T1 is now 2 pi over 5. And how fast should I sample? We've just sort of done this rule of thumb 30 to 60 times in each period of that cyclic waveform, which in this case is now this 2 pi over 5 over 30. Or if I cancel out the pi, is that okay? So that now I have, what, 2 over 50? or 0.04. And for my ultimate sampling, I want to take the minimum of T of omega and T of tau. And I think it was the 0.015, wasn't it? So that's now how fast I would sample. How long would I sample? Now I would be interested in the slowest time constant. Maybe I should call that tau. What was my slowest time constant? I had 2, didn't I? Whoops. I had 1/2 and 1/6. So I take the longest one, or the slowest one. So I'm now simulating for 2.5 seconds, or I might just say round that up to 3. Questions on simulation or simulating? Topic-wise, and we'll finish up, you need to be able to analyze circuits in the time domain, frequency domain, etc. Write the equations. Given a system of equations or a differential equation or some relationship between input and output, you should be able to talk about system properties, whether that's a causal system, whether it's linear or nonlinear, whether it's time invariant, whether the relationship gives you a dynamic system, and what's the system order. Finally, let's just end with this. Filters, you need to be able to determine the order, and that's going to be influenced by how fast you need to roll off, and that could be given many different ways. You should be able to identify types of filters given some kind of transfer function. And we also talked about if we begin with a normalized filter, do you know how to frequency scale? How do you change the bandwidth? And the Butterworth design is the one that we're going to focus on in terms of what's so special about the Butterworth. Gives us our pole pattern, doesn't it? And that pole pattern is nice. It's nice because it's neat in the S-plane. It's symmetric with respect to the origin. Everything is nice that way, but it also gives you a maximally flat pass band. Questions? Hopefully it's clear what's there. It's comprehensive final. It will be 1, 2, 3 exams, that content, and what's been covered since exam number 3. But it'll try to be uniformly distributed. I'm not going to be emphasizing one set of topics more than the other. But I think at this point you can see that I could give you one problem and it could cover everything we've done this semester. I won't do that, but I will give you a large number of problems, probably, maybe 15. So they may not be quite as long as what our exam problems were. Because and they probably won't be multiple choice. Other questions? A, B, C, or D? Good luck with your finals, and I will see you. Please be there Wednesday at 1.